This is the solution to the sample problem in the lecture. We have a 500 kilogram chunk of an unknown metal which has been boiling in water for several minutes is quickly dropped into an insulating styrofoam beaker containing 1 kilogram of water at room temperature, which is set at 20 degrees Celsius. After waiting and gently stirring for 5 minutes, you observe that the water's temperature has reached a constant value of 22 degrees Celsius. A. Assuming that the styrofoam absorbs a negligible amount of heat and that no heat was lost to the surroundings, what is the specific heat of the metal? Second, which is more useful for storing thermal energy, this metal or an equivalent weight of water, and explain. So again, in any physics problem, it would be very helpful if we can visualize the problem. And what better way to visualize the problem than to have it in sketch? Now over here, you have this metal, this one. This chunk of metal is submerged in a boiling water. So of course, if it's boiling water, you must understand that we assume that to be at 100 degrees Celsius at standard pressure. And also, according to that problem, we have something to deduce from that. This is telling us that the initial temperature must also be of the metal, say T sub I of your metal, must also be 100 degrees Celsius since that is submerged in that boiling water. Then afterwards, it's mentioned here na that chunk of metal was transferred. So chunk of metal now is now in this portion here. It's transferred to a water, and the water is at 20 degrees Celsius. And when the metal was transferred, it's mentioned that after some time, so I'm just going to write here, T sub I of the metal initially, as I've said, is at 100 degrees Celsius, but according to the problem, eventually, after 5 minutes, the metal and the water reach a thermal equilibrium, and thus they are at the same final temperature of 22.0 degrees Celsius. So these are some of the things that we can deduce from the problem. Now, when we talk of calorimetry class, always remember that in this case, I want to be very specific. In this case, you have a metal, you transfer it to a water at 22 degrees Celsius, and in effect, the water raised its temperature to 22 degrees Celsius. Now think of it as this chunk of metal has a larger quantity of heat, and that quantity of heat is being transferred towards your water. So in any calorimetry problem, always remember this one. The heat, so plus means the heat that is gained by something is always equal to the heat, actually the negative Q, meaning it's losing heat, the heat that is lost. And why this is the case? Because we consider this system as a isolated system, meaning no heat is exchanged out of the environment, and also no energy is heat energy is energy. No heat or energy is exchanged with the system, and also no mass is exchanged with respect to the outside system. So we only have this interacting bodies here. You have your water and your mass. So whatever the Q that is gained by the system, that should be equal to the Q that is lost by the system. So if you're going to rewrite that one, you'll get this one. Q gained, and then you transpose that one plus Q lost should always be equal to 0. Or another way of thinking about this one, so this is how you should approach calorimetry problem. The Q in the system is just equal to the 0, where the Q in the system explicitly referred to the lost heat. In this case, this is the Q of the metal, because metal is losing the heat in this case. And part of the Q, or the heat of the system, is also the Q gained, which is the heat gained by your water. So once that idea is very clear to you, you can now solve the problem. So basically, what you'll have is that, as I've said, Q that is gained is equal to the heat that is lost. The negative there simply implies that heat is lost. Oh, I can't erase this one. I don't know why that is the case. But anyway, the Q gain in this case is just the Q of the water, since basically water gains the heat. As you can see, it increased its temperature from 20 to 22. And then the Q lost, this is the Q of the unknown metal. So I'm just gonna put M over there. So according to our equation, Q is just M of the water, C of the water, specific heat of the water, and the change of the temperature of the water. And the Q of the unknown metal, or Q sub M, is simply the M of the metal. Sorry, it should be metal. So M sub M, C sub M, and change of temperature of the metal. Now the problem explicitly mentioned that we need to look for the what's this? Specific heat of the metal. So we're looking for C sub M. So when we manipulate that one, this is very easy to do. So you have M of water, specific heat of water, change of temperature of water. That will just be equal to, say, the specific heat of the metal, but that is divided by negative M of the metal. That's the mass of the metal, and the change of temperature of the metal. So right now, we're simply dealing with substitution. The mass of the water, according to the problem, is it's being transferred to a 1 kilogram water. So the metal is transferred to 1 kilogram water. So the mass of the water is 1 kilogram. And the specific heat of water, I'm hoping you are very familiar. It's approximately 4190 joules per kilogram. That Celsius degree, or that Kelvin, it may mean the same thing. And then the change of temperature of your water is, it starts from, I'm just going to write it here, from the final temperature is 22 degrees Celsius, and the initial temperature is 20 degrees Celsius. And this will be divided by the mass of the unknown metal. In the problem, it's very clear that the mass is 500 grams. So we're going to convert that to kilograms. So that's simply 0.5 kilograms multiplied by the change in temperature. Now, in the case of the metal, it achieves thermal equilibrium with water. So they have the same final temperature of 22. So this is 22. I forgot the negative here. 22 degrees Celsius. The initial temperature is, it's coming from the boiling water, so that's 100 degrees Celsius. So when we try to simplify this one, we get 1 kilogram times 4190 joules per kilogram, that's Celsius degree. 22 minus 20 will give us 2 Celsius degree. So as you can see, the Celsius degree would cancel out there. And on the denominator, we get negative 0.5 kilograms. And then 22 minus 100 degrees Celsius will give us, let me do the calculation, that will give us negative 78. Negative 78 Celsius degree. Okay, so from the units above, you'll get Celsius degree would cancel out from the numerators. And then also the kilogram would cancel out here and here. So what we are left with is this one. This is just, if you calculate the top portion, that will give you 8,380. That's unit would be joules. And then the bottom part would be half of 78. So that's 39. Take note that will become positive now because we have negative times negative. So 39 kilogram times Celsius degree. And if you see, the units are right. These are the specific units for specific heat capacity C. So when you further calculate that one, you'll get a value of C that is approximately 215 joules per kilogram, that's Celsius degree. So this is the specific heat capacity of the unknown metal. Now, on the second question, which is more helpful or useful for storing thermal energy? Is it the metal or an equivalent weight of water? So the explanation is pretty easy. You just have to look into the specific heat calculated. So the specific heat of the unknown metal is 215 joules per kilogram that Celsius degree. That means to say this is how we interpret this one. For a 1 kilogram of this metal, and I have to raise that by 1 Celsius degree, I would need 215 joules of energy. However, for water, this one, for every 1 kilogram of water which I need to raise to 1 Celsius degree, I need 4190 joules of heat energy. Therefore, just from the value of C, I could say that water is still more effective in storing thermal energy because it requires more heat energy before raising its temperature. So it's, in a sense, a better storer of thermal energy. So this is how you solve calorimetry problems. Always remember this idea. Whatever heat gained in the system, that is just equal to the heat lost within that system. And this is just telling you na the total heat in the system, since it's an isolated system, is simply equal to 0. But pasabot, if one part of the system is gaining heat, it must be lost by some part or the other part or component of that same system. Okay, so that's it, and I'm hoping this is helpful.